Okay, let's get into it. We're stepping into a market that isn't defined by, blazing speed or luxury, but by ruthlessly executed engineering.
We're talking about the low-speed electric vehicle market, the LSEV.
Exactly. Forget the 800-volt hypercars. This is micromobility, where the margins are razor thin.
And the regulatory landscape is an absolute minefield.
Indeed. And our listener today, who we're treating as the chief systems engineer, has a mission that cuts right to the heart of that tension.
It's a totally different mindset. You're not trying to maximize power density. Here, success is about hitting an aggressive cost target,
And we mean aggressive.
while guaranteeing safety compliance across wildly different global rules.
Right. There's a greenfield platform launch on the line, and your task is to take this strategic report and build out a definitive statement of requirements, the SOR.
For the absolute core of the vehicle, the power electronic system, that's the onboard charger, the DC-DC converter, and the power distribution unit.
All squeezed into one critical 3-in-1 box, the IPU.
And the core tension, as you said, it all comes down to the voltage, the strategic choice.
Do we go with a super simple, ultra-low-cost 48-volt system?
Or do we commit to a globally competitive 96-volt system, knowing full well it triggers a whole cascade of safety costs?
That one choice could make or break the entire platform. We need to find that sweet spot that works everywhere. Europe, the US, Japan, and of course the massive safety-driven A. Woodard class in China.
So let's dive into the source material. Let's really dissect the rules that are forcing our hand here.
Okay, so the first, and I mean the most defining constraint in this whole project, is voltage. Why is the 60-volt DC line so critical? Why is that the number?
It is the great divide. It's the line in the sand for electrical safety and, more importantly, for compliance costs.
The great divide. I like that.
The industry, per ISO 6469, defines anything below 60 volts DC as voltage Class A.
Class A is considered, what, inherently safe?
Inherently safe from lethal direct electrical shock, yes. But the moment you step 1 volt over that 60-volt line, you're in Class B.
And that's where everything changes.
Everything. It immediately triggers a huge mandatory increase in component specs, isolation requirements, and critically active monitoring systems.
And it seems like China, which is the world's biggest market for these things, has basically decided to pull the entire category up into Class B.
Absolutely. The Chinese AATO class, think of the Wuling Mini EV, which sells in staggering numbers.
Right.
It operates well above 60 volts, and it's designed to go faster than 50 kilometers per hour. That immediately forces it to comply with their really stringent GB standards.
Specifically, GB 1384-2020.
That's the one.
Yeah.
It dictates that any B-level voltage system must have active insulation monitoring, an IMD.
And an IMD isn't just a simple fuse. This is sophisticated circuitry we're adding, right?
No, it's very sophisticated, and it's not cheap. The IMD has to continuously monitor the system's insulation resistance.
What are the numbers there?
It has to maintain over 100 ohms per volt in the DC circuits and 500 ohms per volt in the AC circuits. This isn't optional. It's a critical safety measure, especially in a country like China with such varied climates.
You mean high humidity, things like that?
Extreme humidity, extreme cold. Insulation breakdown is a real hazard, and the IMD is designed to give a pre-warning before a fault becomes catastrophic.
So we're adding a whole layer of electronic control to the PDU just for fault detection.
Precisely. And that cost gets compounded by the upcoming GB 30301-2025 standard.
The no fire, no explosion rule.
Exactly. While it's mainly focused on the battery pack, it has a direct impact on the PDU because the PDU is the main disconnect switch.
How so?
It mandates that the PDU has to be able to receive a thermal runaway pre-warning signal from the battery management system, the BMS, and then execute an immediate, totally reliable disconnect.
So now we're talking about integrating things like pyrotechnic fuses or high-speed contactors that have to react in milliseconds.
That's it. It drives your component selections straight towards premium safety-rated parts, which makes that cost optimization goal incredibly difficult.
So the takeaway for China is clear.
The technical implication is you cannot use a cheap 48-volt architecture if you want to sell in volume and offer decent performance. You're legally locked into a system that needs a full high-voltage interlock loop HVIL and IP67 rated connectors.
Which are far more complex and expensive.
Miles more.
Okay, that's China setting a very high bar for safety. Now let's look at Europe, which seems to have this deliberate carve-out for simplicity, the quadricycle framework.
Europe is a stark contrast. The L6E, or light quadricycle class, is the key loophole here.
The Citroën AMI strategy.
The poster child for it. By limiting the vehicle to 45 kilometers per hour and 6 kilowatts of power, they can strategically choose a 48-volt DC battery.
And by staying at 48 volts, they just duck right under that 60-volt threshold. So no HVIL, no complex IMD.
Correct. It's a pure compliance minimization strategy. They bypass all those high-cost protective designs. The PDU becomes basically a simple fuse box and relay system. It's an exercise in regulatory arbitrage.
Perfect for a dense city, but the moment we want to build a global platform that can handle a suburban commute,
You have to step up. You're into the LSEV category, the heavy quadricycle.
which allows up to 15 kilowatts.
Right, and to hit the speeds you need for that market, say 90 or 100 kilometers per hour, you have to use a 72-volt or 96-volt system.
And that pushes us right back into Class B territory,
And triggers UNES Regulation 100, R100.
which, especially in its latest revision, is basically Europe's equivalent of demanding robust high-voltage safety. So it imposes similar cost burdens to the Chinese standards.
Yes, R100 is comprehensive. It requires sophisticated electrical protection, isolation, thermal runaway warnings.
Yeah.
It's a serious standard.
And it also affects charging right.
It does. Our onboard charger has to support European charging protocols, Mode 2 and Mode 3, which means you need PWM communication through the control pilot pin as defined by IEC 618511. Another layer of complexity.
Okay, two other big markets. Japan, with the Toyota C+ pod, chose a really specific high-voltage 177.6 volts. That seems counterintuitive.
Toyota's choice is a masterclass in supply chain strategy. They aligned their high-voltage component needs to leverage their absolutely colossal existing supply chain for hybrid vehicles.
So they're using parts they already buy by the million.
Exactly. It maximizes efficiency while getting economy of scale on proven high-grade hybrid components. Plus, their OBC had to handle both 100-volt and 200-volt AC grid inputs in Japan.
And finally, the U.S. The sources say it has the lowest barrier to entry. Basically, glorified golf carts.
The FMVSS 500 LSV standard is quite permissive historically. 48 or 72 volts was common, but the market is evolving.
People want more now.
U.S. consumers are starting to expect level 2 charging with a proper SAE J1772 plug, and they want higher speeds. That demand is pushing the U.S. platforms inevitably towards 72 to 96 volts. It's pulling them closer to that global Class B mandate.
Okay, so regulations and market demands are all pushing us away from the simple 48-volt option. So let's lock this down. Why is 96 volts with a working range of, say, 60 to 120 volts the non-negotiable sweet spot for our global platform?
It's the optimal intersection of performance and component cost.
Okay.
If you want 80 to 100 kilometers per hour, 96 volts gives you the power you need without excessive current. But the critical financial advantage is in the components you can use.
The semiconductors.
Specifically, at 96 volts, we can use highly optimized, mass-produced 100 to 150 volt silicon MOSFETs across all the power converters.
And what financial cliff are we avoiding by staying in that 150-volt range?
We are avoiding the massive jump to 650 volt components. Full-size EVs need expensive, specialized 650-volt IGBTs or even silicon carbide MOSFETs.
And those are orders of magnitude more expensive.
Even at volume. So 96 volts lets us meet global speed requirements while using the cheapest, most available power semiconductors on the planet. This is the absolute foundation of hitting our aggressive BOM target.
That settles it. The 96-volt decision is frozen. Now we can dig into how the competition is built around these constraints. All right, let's start with the cost leader, the Wuling-Hongguang Mini EV. It really does set the benchmark. The report notes they use a 96 to 115-volt architecture. What's the core engineering benefit there for cost, beyond just meeting the regulations?
It's purely about reducing current. It comes down to the basic physics. Power equals voltage times current.
P equals V times I.
Exactly. If you want to deliver, say, 15 kilowatts to the motor, doing that at 48 volts requires massive copper cables and extremely high current contactors.
It's a brute force approach.
It is. By operating closer to 100 volts, Wuling effectively halves the current they need compared to a 48-volt system.
And less current means.
Thinner, cheaper copper cables, lighter connectors, lower-rated chipper contactors all through the vehicle. The savings on copper alone, just in the high-voltage harness, is substantial.
So how do they manage to meet those strict GB safety rules while keeping costs so incredibly low?
They leveraged highly integrated systems. They sourced their 3-in-1 IPUs from specialized domestic suppliers like Ticheng or DeLong.
So they didn't develop it in-house.
No, they went to experts. This intense integration minimizes all the external high-voltage cabling and eliminates several expensive HV connector pairs between the different modules.
But the report did include a warning, right?
Yeah.
About how they achieved some of that cost.
Yes, a critical caveat. The analysis noted signs of extreme cost-cutting, like a reliance on manual internal wiring assembly. That suggests potential trade-offs in long-term reliability and build consistency, which is a risk we have to mitigate in our own design.
Okay, let's pivot to the other end of the spectrum, the Citronomy, the regulatory minimalist.
Right. If Willing is about achieving safety compliance at maximum volume, the AMI is about maximum regulatory avoidance.
It's a perfect example of engineering to the rulebook, not for performance.
Exactly. Its 48-volt architecture means it operates entirely outside of Class B. They are essentially treating the powertrain like a very advanced enclosed golf cart.
So the PDU is radically simplified. No HVIL, no sealed contactors.
None of it. They can use standard automotive-grade components where possible. It's an entirely different philosophy.
And that philosophy carries right through to the charging system.
It does. The OBC is a very simple, non-isolated, low-power unit around 2 kilowatts. It often uses a standard household plug.
A Schuko plug.
Yes. It completely bypasses the complexity and cost of Mode 3 communication protocols and Level 2 charging. It's cheap, it's simple, and it works for the L6E mandate. But it definitely limits its appeal and export potential.
Okay, moving on to the Toyota C Plus Pod, the high-end niche. We know the 177.6-volt choice was driven by their supply chain, but what unique technical feature did Toyota build into their power core?
The explicit integration of vehicle-to-load capability, V2L.
So you can power things from the car.
Right. The Japanese market has a unique demand for resilience, for the vehicle to serve as a power source during grid outages. Toyota system supports 1,500 watts of external AC power.
And building that in isn't trivial.
Not at all. Integrating that bidirectional power flow demands really robust power electronics and high-grade safety isolation. It definitely elevated the engineering complexity and the perceived value of the vehicle.
Finally, the Polaris GEM E4 in the US, the legacy LSV. Why does that older architecture just not work for what we're trying to do?
The GEM uses the old-school discrete component method. You have a separate box for the charger, a separate box for the DC-DC, a separate one for the motor controller.
Which sounds like a nightmare for assembly and packaging.
It is. It immediately inflates the bill of materials with redundant housings, brackets, and, crucially, all the high-voltage wiring needed to connect everything. It's complex, it's heavy, it takes up space, and it's more prone to failure because of all the extra connectors.
So that architecture just can't hit our cost targets.
Not even close. It can't hit our cost, our volume, or our reliability targets.
So if we look across this whole comparison, Willing, AMI, Toyota, Polaris, the single most important takeaway, the absolute mandate for our chief systems engineer, has to be integration.
Without a single doubt. Willing and Toyota, from different ends of the market, both prove that a highly integrated 3-in-1 IPU is the only way to go.
It's the only path to hitting both cost efficiency and safety compliance at volume.
Our 96-volt choice already forces us to include all the mandatory safety features like HVIL and isolation. That means a 3-in-1 IPU is the only viable path forward for a global product that can hit that sub-$220 MUBON cost.
That sets the mandate. Now let's get into the physical execution of this IPU. How do we actually build this thing and manage all the heat it's going to produce?
So the core requirement is clear. The 3-in-1 IPU, OBC, DC-DC, and PDU all consolidated into a single IP67-rated die-cast aluminum housing.
And this isn't just about neat packaging, is it? You said it's the financial backbone of the project.
It absolutely is.
So let's break down those savings. The report estimates $50 to $100 per vehicle. Where exactly does that money come from?
It comes from a few places, but primarily from eliminating high-voltage cables and those specialized Class B connectors.
How much can one of those connectors cost?
A dedicated HV connector, especially one that's IP67 rated and has those mandatory last mate, first break HVL pins, can easily cost $10 to $20 a piece.
And we're eliminating how many?
3 or 4 pairs. So right there, you could be saving $40 to $80 immediately. Then you have the high-voltage cables themselves, which are thick, expensive copper.
Right.
By internalizing those connections, you're replacing feet of expensive cable with short, cheap, low-resistance copper bus bars inside the unit.
And then there's assembly time.
Exactly. Installing one box with one main HV interface is way faster than installing and connecting 3 separate units on the production line. It's a huge time saver.
So integration isn't just an engineering preference, it's a critical financial lever to hit our sub-$220 VO-BRAM. And what about the physical size? We're tight on space.
Extremely tight. We have to target a total volume of less than 5.0 liters and a weight under 6.0 kilograms.
That is an incredibly high power density, considering what's inside.
It is. And the housing itself has to be ADC12 die-cast aluminum. That's crucial for mechanical strength, EMI shielding, and for acting as the primary heat sink.
You mentioned IP67, which is dust-proof and submersible. But the report recommends pushing the connectors to IP6K9K. Why that extra level of protection?
You have to think about the vehicle's entire life. IP6K9K means it can resist high-pressure, high-temperature steam cleaning jets.
Like from an industrial power washer.
Exactly. Think about a vehicle used in a logistics fleet or by a city municipality. They get cleaned aggressively. A standard IP67 rating can fail under that kind of direct high-pressure spray, especially around the connector seals.
And water getting in there would be a disaster.
A very expensive warranty claim. Specifying IP6K9K upfront saves millions in long-term reliability costs. It's a must.
Okay, now for the big one, the most contentious decision. Liquid versus air cooling. Given the cost pressure, air cooling just feels simpler and cheaper. Why does the report mandate liquid cooling for anything over 3.3 kilowatts?
It's a decision that's really driven by physics and the packaging constraints we just talked about.
Yep.
First, thermal capacity. A water glycol liquid PIX is roughly 4 times more efficient at transferring heat than air is.
4 times.
Yes. So to get rid of 3.3 kilowatts of heat using just air, in a box smaller than 5 liters, you would need heat sinks that are physically too large to fit.
So the volume constraint alone basically rules out air cooling at higher power.
It makes it almost impossible, but the second factor is arguably even more critical: reliability and sealing.
The IP67 rating.
To get to IP67 with an air-cooled system, you need complex internal air channels, or you have to rely on heavy potting compounds. It's complicated and expensive. With liquid cooling, you can have a simple external cooling plate, and the entire enclosure can be completely hermetically sealed.
So trying to keep a fan-cooled unit sealed for 10 years is just a losing battle.
It's a nearly impossible sealing challenge, so liquid cooling isn't a premium feature here. It's actually the cost-effective way to enable high power density and meet our mandatory reliability targets.
That makes sense. And finally, the digital side. It's 3 systems in one box, but it has to talk to the vehicle as a single unit.
It must present itself as a single coherent CAN 2.0B or SIA NFD node. This simplifies the vehicle's wiring harness and, critically, the software stack.
And for diagnostics.
It has to support Unified Diagnostic Services, UDS. That's the standard protocol that lets technicians, or our own R&D team, diagnose faults and perform over-the-air updates. It's non-negotiable for any modern vehicle.
The structural SOR is now firm, 96-volt IP67 liquid-cooled, 3-in-1 IPU. Let's move to the heart of it. The electrical engineering specs for the OBC and DC-DC.
All right, the onboard charger, the OBC. This has to be the workhorse of global compatibility, and the biggest challenge is the universal input design.
You mean being able to plug it in anywhere in the world?
Exactly. It has to handle everything from an 85 VAC minimum input up to a 265 VAC maximum.
That 85-volt minimum is tough. That's for the Japanese 100-volt grid and, I guess, brownout conditions on the US 120-volt grid?
Correct. And that low input voltage presents a real engineering challenge for the first stage of the converter, the power factor correction stage.
Why is that?
Because when the input voltage is low, the current demand for a fixed power output, say 3.3 kilowatts, becomes extremely high. And high current means you need beefier components, bigger inductors, MOSFETs with very low on resistance to avoid massive efficiency losses right at the start.
And our targets are ambitious: 3.3 kilowatt standard with a 6.6 kilowatt option and peak efficiency over 94%. So, topology. We need cost efficiency. Why are we recommending the interleaved boost PFC over something more efficient, like a bridgeless totem pole PFC?
The bridgeless totem pole is, you're right, undeniably more efficient. But it requires highly complex control schemes and, crucially, very expensive power switches. You're talking gallium nitride or silicon carbide.
Which is just not in the budget for an LSEV.
Financially impossible. So the interleaved boost PFC is the practical strategic choice. It uses standard, much cheaper silicon MOSFETs.
And interleaved means it has multiple stages working in parallel.
Exactly. You have 2 or more boost stages running out of phase. This lets you spread the thermal load across multiple cheaper components so your heat sinks can be smaller.
And it has other benefits too, right?
The big one is that it dramatically reduces the input current ripple. That means your filters can be smaller and cheaper, and your EMI performance is much better right out of the gate. It's a mature, reliable topology that's perfect for hitting our cost target.
Okay, that's the PFC stage. Now for the AC to DC isolation stage. What's the best choice there to balance efficiency and EMI in such a dense package?
The LLC resonant converter is the mandated choice for the isolation stage.
Why LLC?
Its key advantage is achieving what we call zero voltage switching, or ZVS, across a very wide range of loads.
Which means the power switches turn on when there's no voltage across them.
Precisely. This minimizes switching losses, which means less heat. That's a direct path to hitting our 94% efficiency target, and it reduces the thermal load in our tiny ITU. Plus, the LLC's smooth current waveform gives it superior EMI performance compared to hard-switched converters like a phase-shifted full bridge.
And on the output side, we're at a low 96 volts, but with high current. How do we avoid losing all our efficiency there?
Mandatory synchronous rectification. That is a non-negotiable requirement.
So we're replacing the output diodes with MOSFETs.
Yes. Traditional diodes have a forward voltage drop that wastes a ton of power, especially at high current and low voltage. By using actively controlled MOSFETs instead, we can cut those conduction losses dramatically. It's essential for meeting the efficiency target.
Finally, we need to support V2L, vehicle to load, up to 2.2 kVA. How does adding that bidirectional capability change the design?
It transforms the OBC from a simple charger into a fully functional grid-tied inverter when it runs in reverse.
So the power has to flow backwards through the whole thing.
Exactly. The LLC converter has to be able to push power backward. This requires sophisticated control of those synchronous rectification MOSFETs. They have to actively invert the DC power. Then that inverted DC is fed back into the PFC stage, which has to reverse its function and act as an AC inverter. It's a significant layer of control complexity.
Okay, now for the DC-DC converter, the alternator replacement. What power rating do we really need? The report says 1.0 kilowatt continuous, 1.5 peak. That feels pretty beefy for a micro EV.
That robustness is critical for safety and for operational margin. These aren't simple carts anymore.
What are the big 12-volt loads?
You have electric power steering, which can pull 300 watts, an electric brake vacuum pump, another 100 watts, the HVAC fan, maybe 200 watts, plus lights, infotainment. During a cold start or a hard turn, the instantaneous 12-volt demand can easily top 800 watts.
So the 1.0 kilowatt rating is a necessary safety buffer.
It is. It prevents the 12-volt battery from being discharged under heavy load, which could lead to critical system faults.
We already established that the topology must be isolated. A non-isolated buck converter is way cheaper. Remind me why that's an absolute no-go under the safety standards.
Because of the catastrophic failure scenario. If you use a non-isolated buck and a key component like a MOSFET fails short.
The full 96 volts from the main battery gets dumped onto the 12-volt system.
Instantly. It would be a lethal shock hazard for anyone touching the car and would destroy every single 12-volt electronic component. A mandatory isolated topology uses a physical transformer barrier, so that can never happen. It's an absolute safety requirement.
And what about electrical noise, EMI?
EMI compliance is paramount. The DC-DC can be a huge source of noise. We have to meet CSPR 25 Class 3, but the SR recommends targeting Class 5.
Why aim higher?
Because failure to do so can lead to radio interference, GPS signal loss, all sorts of hard-to-diagnose field issues that destroy customer perception. Robust internal filtering and shielding from the ADC-12 housing are key.
And one last point, flexibility. Why does it need to support parallel operation?
For specialized versions of the vehicle. Think of a delivery van or a utility vehicle built on the same platform. They might have much higher 12-volt loads. The IPU has to be engineered so that two DC-DC units can be run in parallel, sharing the load equally. It's vital for the platform's commercial viability.
All right, let's talk about the PDU, the power distribution unit. This is the safety nerve center. And for our 96-volt system, the high voltage interlock loop, or HVIL, is its core function. Walk me through exactly how HVIL works.
The HVAL is a fail-safe. It's a continuous low-voltage monitoring circuit, usually 12 volts, that's threaded through a dedicated pin in every single high-voltage connector.
And its only job is to check that everything is plugged in tight.
That's its only job. If the loop is closed, State A, the PDU, knows the system is mechanically sound. If that loop opens for any reason, a loose connector, someone pulling the service plug, that's State B, the PDU has to interpret that as an immediate hazard.
And the response has to be incredibly fast.
Mandatory response time is under 50 milliseconds. The PDU detects the open loop and immediately commands the main contactors to open, disconnecting the battery from the entire high-voltage bus.
So it de-energizes the system before anyone can touch a live component.
Instantly.
This whole logic really hinges on the mechanical design of the connectors themselves. Explain the last mate first break design.
It refers to the physical length of the pins. When you're unplugging a connector, the shorter HVL auxiliary pin has to be the very first physical contact to break.
So the safety signal's cut first.
It signals the PDU to cut the main power before the longer, high-current power pins can fully disengage and cause a dangerous, high-energy electrical arc. And the reverse is true when you plug it in. The HVL pin is the last to make contact, so power is only enabled once the connection is fully secure.
It's a simple but brilliant mechanical safety feature. Now, the pre-charge circuit. This is to stop the main contactors from welding themselves shut, right?
Yeah. Exactly. We have to prevent a massive inrush of current when the system starts up. So you need a dedicated pre-charge relay and a big, high-power ceramic resistor, usually 50 to 100 ohms.
How does that sequence work?
When you turn the vehicle on, the pre-charge relay closes first. It gently charges up the big capacitors on the bus through that resistor.
And there's a time limit for that.
The whole process has to complete within 500 milliseconds. The PDU monitors the bus voltage. Only when it reaches 95% of the battery voltage does the main contactor close, bypassing the resistor for a soft, safe connection.
What about the contactors themselves? We're at 96 volts and potentially 250 amps.
So we need two main contactors, positive and negative. They have to be rated for 250 amps continuous and a minimum of 450 volts DC withstand.
And they can't just be standard automotive relays.
Absolutely not. Because it's DC, you need specialized arc extinguishing. That means the contactors have to be hermetically sealed, either gas-filled or ceramic sealed, to prevent a sustained arc from melting the contacts.
Infusing.
We need multiple fuse paths inside the PDU. A big primary traction fuse, maybe 350 to 400 amps, fast-acting. Then smaller auxiliary fuses for the OBC and DC-DC branches, say 20 to 40 amps. And of course, the manual service disconnect, the MSD plug, has to be integrated with its own HVIL breakpoint.
Okay, finally, the mandatory active insulation monitoring. How do we actually validate that our IPU's control board is doing this correctly?
The IMD has to be able to measure from 0 up to 10 megaohms of resistance with an alarm threshold set below 500 ohms per volt.
And we test this by simulating a fault.
Exactly. Engineers will use specific methods like a bridge method or low-frequency current injection to measure the impedance between the high-voltage bus and the vehicle chassis. We have to prove it works under all conditions.
Speaking of testing, the SOR lays out a really tough validation gauntlet. Let's start with the electrical endurance test, the dielectric withstand.
The high pot test. This is the ultimate test of the unit's electrical barriers. We apply 2500 volts DC between the high-voltage circuits, the 12-volt circuits, and the chassis for 1 full minute.
And you're looking for any leakage.
The leakage current has to stay below 5 milliamps. This confirms that all the physical insulation, the potting, the clearances, the transformer isolation is robust enough to prevent a lethal failure.
And what about physical toughness? For global export, these environmental tests are crucial.
Absolutely. The 720 hours of neutral salt spray testing is mandated. It simulates years in a coastal environment or on heavily salted winter roads. It confirms the corrosion resistance of the casing and the connectors.
Then there's vibration.
Yeah.
You mentioned LSEVs are notoriously stiff.
That's a critical point. They have less sophisticated suspensions, so the power core takes a much bigger beating from the road. We have to pass the ISO 16753 random vibration tests, which simulate a decade of severe use. We have to ensure no solder joints crack.
And the final durability checks, thermal cycling and HTOL.
We have to prove it can survive extreme temperature swings. That means 1,000 thermal cycles, from minus 40 Celsius all the way up to plus 85 C, while the unit is powered and loaded. That's high-temperature operating life. 1,000 hours running at max load with the coolant temperature held at 85 degrees Celsius. These tests prove the integrated design and the liquid cooling system can handle the absolute worst-case scenario for the vehicle's entire lifespan.
So we have just defined a remarkably sophisticated power system. 96 volts, liquid-cooled, fully integrated, and packed with mandatory safety features. Now we have to confront the commercial reality. All of that engineering has to fit under an incredibly aggressive cost ceiling.
The cost target is the master constraint. For this platform to have any chance, especially against players like Wuling, the total bill of materials cost for this entire IPU has to be targeted at less than $220.
$220. That is an astonishingly low number, considering everything we just mandated: sealed contactors, active IMD, high-spec MOSFETs.
It is. It forces a massive cost reduction compared to what's available from Western suppliers.
What does that contrast? What would this unit cost from a Western Tier 1?
If you were to go to a Delta, a Vallejo, a Bosch for a comparable fully compliant IPU, you would be looking at an FOB price somewhere between $500 and $800 per unit.
Wow.
So our target range of $180 to $250 FOB China is absolutely necessary for the vehicle to be viable. Every single component choice has to be optimized against that $220 ceiling.
Okay, so given that complexity and our rapid greenfield development schedule, is it even feasible to develop this hardware in-house?
Absolutely not. The time to market would be too long, and the validation risk is just far too high.
So the strategy has to be procurement.
The strategic recommendation is clear. We must procure a mature, highly optimized, white-label 3-in-1 unit. We have to leverage the expertise and the massive component volume of the established Chinese supply ecosystem.
Which specific suppliers should the engineering team be targeting for their request for quotation?
You go straight to the leaders who have already mastered this. We should be targeting Ticheng or Shinry, or key suppliers to Wuling, and have off-the-shelf 96-volt IPUs. DeLong New Energy is another great option. They focus specifically on high-integration OBC DC-DC solutions, and for a higher-performance L70 variant, we should engage Innovance.
Okay, so the action plan needs to be formalized now. What is the immediate, non-negotiable next step for our chief systems engineer?
First, platform freeze. The entire powertrain architecture has to be defined around a 96-volt, 30-cell lithium iron phosphate battery pack configuration that has to be locked.
And second,
Immediately issue a highly specific RFQ. It has to target a liquid-cooled 3-in-1 IPU with the 3.3 kilowatt OBC and 1.5 kilowatt DC-DC. And it must explicitly confirm that it has integrated HVIL and active insulation monitoring to meet both the Chinese GB 10384 and the European UN R100 Rev 3 standards right out of the box.
so we secure compliance and cost leadership before we even think about cutting any metal ourselves.
That's the only way to launch on time and on budget.
This deep dive has really stripped away the hype around micro-EVs and just exposed the raw engineering challenge. It's a fight against physics, finance, and frankly, a mountain of regulatory complexity.
We started with that core tension of the LSEV market, that constant battle between extreme cost optimization and non-negotiable global safety.
And we really hammered out the three strategic pillars for the statement of requirements.
First, locking the architecture onto that 96-volt sweet spot. It gives us the performance we need while avoiding the huge financial burden of 650-volt components.
Second, making that mandatory switch to the IP67 liquid-cooled 3-in-1 IPU. That move alone secures critical space savings and hits that estimated $50 to $100 per vehicle savings on cables and connectors.
And third, the inescapable safety mandate. Full HVIL, the isolated DC-DC, active insulation monitoring, all features driven primarily by those high-volume Chinese standards, but essential for compliance everywhere.
And adhering to this incredibly detailed SOR is really the absolute minimum requirement for launching a viable platform, isn't it?
It is. If you're any less rigorous, the platform will either be immediately non-compliant in a critical market, or it will simply be priced out of the competition because you missed that sub-$220 BOM target.
We spent some time on the Toyota C+ Pod's strategic inclusion of vehicle-to-load. And we know it's possible because our mandated OBC topology supports that bidirectional power flow.
We know we can engineer it.
But that engineering question leads to a much bigger, more strategic question for the future.
If LSEVs have to win on cost, they also have to win on value. They need a proposition that goes beyond just being a simple city runabout.
Right.
We have built the technical capability for two-way power flow into the core of this vehicle. So how might microgrid features, using this integrated cost-optimized IPU, to position the LSEV not just as a vehicle, but as a temporary localized power hub for emergency relief or remote work sites, how might that become the next critical feature engineers must market to justify the LSEV's existence as a multi-purpose energy asset? That's the strategic challenge waiting in the next phase.